and I'll share my screen and we'll get going. Okay, can everyone see the slides?
Yes, sir.
Okay. So today it's all about radiated susceptibility electric field, otherwise known as RS103. Here is a list of the topics that I'll be talking about. So there's a lot there, so let's get rolling. So just a review of some of the things I've talked about in previous sessions. Just I always like to remind you of what is the raison d'etre of any given test or group of tests. So the raison d'etre for RE102 is to protect antenna connected radio receivers from your equipment as the culprit. And the raison d'etre of RS103 is to protect your equipment from intentional transmissions from antenna connected radio transmitters. Those are the stated reasons for these tests. They are not meant to be compared directly against each other. So you're not, it is not intended to compare the radiated emissions limits to the radiated susceptibility limits. They are two different things. Don't do this. And we've gone over this many times. So, but just emphasizing verbiage directly from the mill standard. Saying the same thing here. There's no implied relationship between RS103 and RE102. It may be desirable to tailor the frequency coverage of the limit to include only frequency bands where antenna-connected transmitters are present. So that's generally above 200 megahertz for Goddard platform. And just to emphasize again that the cables are part of the EUT. So, so my mistake here. This is a carryover from radiated emissions. I thought I'd updated all the references to say susceptibility, but I missed this one. But it's the same idea that you're assessing radiated susceptibility from the EUT and associated cables. The cables are very much part of the EUT. So this is a review of a chart I've shown before. Just that common mode energy will couple onto the cables and radiate. And then incident radiated energy will couple onto the cables and be carried into the EUT. And below 200 megahertz, if you don't have any radio receivers or transmitters operating below 200 megahertz, the dominant concern is crosstalk, which are much more efficiently addressed with direct measurements of common mode currents using CMCE and CMCS, which we've covered in previous sessions. So the basic RS103 test method, the applicability, it applies to equipment and subsystem enclosures and all interconnecting cables. That's directly out of the mill standard. And then the purpose of the requirement is to verify the ability of the EUT and associated cabling to withstand electric fields generated from intentional RF transmitters. Those are the key points there. Cabling, and that it's about withstanding electric fields from intentional RF transmitters. That's a very central point, and I'll keep beating that to death because it needs to be. And then again, just no implied relationship between RS103 and RE102. Just making sure the point doesn't get lost. Everyone tells me not to use red text unless it's something that you're beating people over the head with, and that's what I'm doing here. So I'm using red text. And then we use CMCE and CMCS to evaluate crosstalk. Okay, so a few more notes about the basic test method. This diagram is right out of the mill standard. So not too surprisingly, the centerpiece of the test method is a test antenna or a transmitting or radiating antenna to illuminate the EUT. You're applying an intentional radiated field as your stimulus to see how the EUT responds. So the different antennas, at least that we use at Goddard, different labs may use different antennas. This is less specified than RE102. RE102 said, it identifies specific antennas to be used in the different frequency ranges. That's less specific here, but there are some general, some antennas that do tend to be used rather consistently. So in the low frequency range, there's the parallel element. That rod antenna we use for RE102, just that's receive only. I mean, that is not intended to be a transmit antenna. You can't handle the power that you would need to put into it. So we have this parallel element that we use in the 10 kilohertz to 30 megahertz range. The biconical antenna is fine to also use as a transmit. Well, it's fine in terms of being reciprocal, that if you're using it as a receive antenna, you can use it as a transmit antenna as well. However, these two antennas should only be used if you have intentional transmitters operating in these frequency ranges. If not, then we don't generally test in these we don't generally test RS103 in these frequency ranges. We use our common mode conducted emissions and susceptibility test. So to emphasize this point a little further, recall the wavelength in meters equals 300 divided by the frequency in megahertz. That's just another way of writing c over f, the speed of light in free space or air, divided by frequency. C over f is just 300 times 10 to the 6th divided by frequency. So 300 divided by frequency in megahertz is just shorthand for that. So just looking at these numbers here, in the parallel element range, you're dealing with wavelengths of 30 kilometers down to 10 meters. And in the biconical or bow tie range, you're dealing with wavelengths of 1.5 to 10 meters. So at least for the upper end of the parallel element range and the entire range of the biconical, you're dealing with wavelengths that are comparable to typical chamber dimension. And especially when you look at either half wavelength, potential half wavelength or quarter wavelength resonances, and the anechoic materials generally are more effective at higher frequencies. Now, your ferrite tiles that you might have behind some of the this type of anechoic material, those tend to work pretty well at lower frequencies. But absent that, if all you have are these more conical type of anechoic materials on your walls, those might not kick in until maybe the upper end of the bicon range, and maybe even higher. So, all of this compounds to make constructive and destructive interference very likely in these frequency ranges, and we've seen it happen. And this is not an issue for your common mode testing. This is a big part of why. Well, the main reason is if you don't have any transmitters operating in this frequency range, it's just not a very meaningful test. But this is another reason to emphasize the conducted testing below 200 megahertz, that you don't have to grapple with these kinds of issues with constructive destructive interference, because of you're dealing with wavelengths that are comparable to your room dimensions. All those issues just go away if you just are dealing with the measuring currents directly. You're just far less susceptible to room resonances and things like that, making for a less reliable and predictable test result, and repeatable. So moving right along, above 200 megahertz, from 200 megahertz to 1 gig, we use the large double ridge guide horn antenna. And then above 1 gigahertz, we use the small DRG horn. So I'm just going to call them DRG from now on, but double ridge guide horn is what that stands for. And you see the basic construction is pretty similar. They're your double ridges to scale, kind of, but so we'll see pictures of these here. Actually, I may not have included them in this, but when we do the workshop, we'll show you these things. This thing is about roughly a meter square. Obviously, it's not totally square. It's about a meter across, and this one, well, it's much easier to hold in your hand. It's maybe a foot across or something like that. Anyway, so then the other part of your test setup is the electric field sensor. You need to have something that is detecting and sensing the electric field that you're applying to provide you that feedback of the level that you are actually applying to the UT. So this is clearly a crucial part of the test setup as well. So here are two typical types of electric field probes. I just grabbed these pictures off the ETS Lindgren website. I'm not sure if they're the specific models we use at Goddard, but we use models that look very much like this. This one is very clearly a 3-axis probe, so you can actually display the electric fields in X, Y, and Z axis. I believe this one is as well. It just doesn't look as obviously like it. But you can configure your setup to look at all 3 axes individually, or just give actually, I believe that should really be RS. That's root sum square axis value. So moving right along, here is the default limit table from Mil Standard 461G for RS103. Many different applications here, aircraft, ships, and so forth. Space is the last column, and not a whole lot of variety here. They just specify 20 volts per meter across the whole frequency range by default. Now, that's what Mil Standard says. Okay, so let's look at what we put in GEVs. That for equipment that must operate at launch, we go ahead with that minimum level of 20 volts per meter from 2 megahertz to 18 gigahertz. This is from, I think I must have missed updating this in the last version of GEV. So from everything I just said, the default would be 200 megahertz and above, unless you had specific transmitters operating lower than that. Okay. And then there's some additional guidance in this ELDL document for guideline for spacecraft launching from Eastern, Western, Pacific, and Pacific ranges. But as always, you have to look at your mission-specific documentation. So anything specific to your launch vehicle and launch site, specific transmitters used on the vehicle itself and at the launch site, that has to be incorporated into your test plan, right? The people come and ask me what levels should we be testing to? Like, well, that needs to be specified by your program, right? Different launch sites are going to have different transmitters, and so that's what you have to use to specify what you're testing to. The 20 volts per meter is really just a starting point. Some of these launch site levels go much higher than that, and you have to pay attention to that in your mission specific or launch site specific documentation. So for equipment that is not powered on during launch, like your science payloads and such, the minimum levels we recommend are 2 volts per meter. Again, I clearly missed updating this, but that really should be 200 megahertz and above. Again, project documentation, it's mission specific. If you have some reason to test the different levels, then that's what you need to incorporate. Now, looking ahead a little bit, 2 volts per meter is a very low level to test to. The background levels that we generally sense with our electric field sensors are pretty close to that, somewhere between 1 and 1.5 volts per meter, or even pushing 2 volts per meter. Just you're probably bathing in pretty close to 2 volts per meter from just the lights in your office and anything else. So it's not a very stringent level for one thing, but it's also it can be a difficult level to test to. Sometimes we just, even if the requirement is 2 volts per meter, we've sometimes, and I've heard other test houses say they just bump it up to 5 volts per meter because that's a much easier level to consistently level on. That it's enough above the noise floor that they can level on it much more quickly, and it's still a pretty benign level. So something else to pay attention to. So your mileage may vary. You must do your homework. Consistent message throughout all this is the radiated environment comes from your mission specific documentation. So another note here, just read this verbatim. Based on data and analysis compiled by the Department of Defense Joint Spectrum Center, That is actually abbreviated to JSC, and that sometimes gets confused with Johnson Space Center. Clearly not, it's a different beast. The on-orbit RF environment can likely exceed 2 volts per meter in specific frequency bands due to fields transmitted from high-gain antennas on the ground or on communication satellites. So the susceptibility test levels must be derived from the expected mission environment. And so some guidance is provided in that JSC document. That's Joint Spectrum Council. And but something to note here is these larger fields are generally of a brief duration, like milliseconds, maybe to a couple of seconds, caused by the spacecraft passing over a large ground-based antenna with high gain. So if it's high gain, it's a narrow beam, so you're not necessarily bathing in it, you're passing through it in a pretty short period of time. So even if you're seeing, possibly hundreds of volts per meter, it's for maybe a few tens of milliseconds, or so hundreds of volts per meter for a few tens of milliseconds versus 2 or 20 volts per meter continuously are two different problems. So if you're looking at these levels of a few hundred volts per meter, and you're trying to implement a solution to just being bathed in that level indefinitely, that's going to drive you to some very expensive and unnecessary solutions, as opposed to just realizing that you may only be exposed to those levels for a few tens of milliseconds at a time. But there again, you got to do your homework and make sure you're doing what's necessary and not engaging in overkill. So some general notes on susceptibility testing for the MIL standard. This table 3, the MIL standard 461G, specifies scan rates and step sizes for susceptibility scans. This includes conducted as well as radiated. And I don't know that I've ever actually participated in a test that used analog scans. But this is specifying your analog scan rate. Generally speaking, we're doing step scans, and these are the step sizes. So if we look at an example here, starting at 1 gigahertz, to make the math easy, the MIL standard specified step size is 0.25%, 0.0025 f0. Well, what does that mean? So if we start at 1 gigahertz, our next frequency is just 1.0025 times that. So 1.0025 gigahertz. Then the next frequency is 1.0025 times that, which is 1.005 plus a lot of other digits I'm not going to read. But you get the idea. And then you just keep going until you get to, our default stopping point is 18 gigahertz. So if you do the math, I did, because of course I'm a mathicist. The from 1 to 18 gigahertz, that's a little under 1,200 frequency steps. And the default dwell time per step for the MIL standard is 3 seconds. So just looking at 3 seconds per step, we'll talk about overhead here coming up shortly. But just looking at that, you're looking at about an hour to do one of those sweeps. Now with the overhead, you're probably looking at doubling that time or more. But if we just look at it, you're looking about an hour to do those sweeps. Well, so in GEVs, we've relaxed that step size above 1 gigahertz to 1%, 0.01 f0. So there, we start at 1 gigahertz, our next frequency is 1.01 gigahertz, our next one is just over 1.02, and so on. So there, from 1 to 18 gigahertz, we're looking at, not too surprisingly, about 1/4 of the number of steps. So about 1/4 of the time, about 15 minutes. And then if a 1 second dwell time is sufficient, which we generally apply on Goddard missions, the scans may be shortened even further. But radiated susceptibility is, I think, well, certainly my experience, it is the single most time-consuming test that we have. And I think especially the above 1 gigahertz because of this fine step size that's defaulted per the MIL standard. So in GEVs, we've relaxed that, given a factor of 4 relaxation, I don't think any significant loss in the value of the test. I think the likelihood that you're going to miss something with these relaxed step sizes is very small, I think. Nothing's stopping you from using this step size if you want to, but this just permits you to relax it a little bit and make a little more efficient use of test time. A little review of modulation. Did talk about this in an earlier session, but I think this bears repeating. The default in the mill standard specifies that for CS114 and RS103, that the test signal shall be pulse modulated at a 1 kilohertz rate with a 50% duty cycle. So if you start with a continuous wave, or in vernacular, or not really vernacular, it's generally just abbreviated as CW, just a continuous sinusoid, CW signal, that's what that means. Then you apply a 1 kilohertz pulse modulation, a 50% duty cycle, and that means you're on for 500 microseconds and off for 500 microseconds. Okay. So implications for what my most direct experience with this is with detector and imaging systems. The first order, the noise, or any undesirable signal picked up as a result of your susceptibility signal, is determined by taking statistics on pixel data, or mean and standard deviation of sample pixel values, generally with respect to a reference frame without your perturbing signal applied. So for a typical pixel period of 10 microseconds, that's a sampling rate of 100 kilohertz. Any frequency above 50 kilohertz will be undersampled. It'll be alias, right? So most of the radiated, and that's most of the radiated susceptibility frequency range. And especially if we start at 200 megahertz, it's all of it. Everything is going to be undersampled and aliased. So the susceptibility at any given frequency will manifest itself as the total energy integrated over a pixel period. Right? If you're going to have multiple cycles of your perturbing signal over your pixel period, you're not going to get this sinusoid. You're just going to get some flat level of here's the total amount of energy that pixel has seen in that 10 microsecond period. So at a susceptible frequency, an unmodulated or CW signal will produce an approximately equal shifted signal level in all pixels. And performing statistics on such frames may show a shifted mean, but the standard deviation will not look much different from a non-RS frame. This is direct experience talking here. We went through a test some years ago where we forgot to apply some modulation, or we just didn't. I mean, it was a test in the lab. If it was a full-up official test in the EMI lab, we would have applied the modulation, right? But this was just a diagnostic test in a lab. And we were seeing it appeared that we were not seeing any interference when everything told us that we should. We should definitely be seeing some interference from this applied signal. And it was because of this very thing that, because a CW signal was causing the same shift in all the pixels, the statistics were not showing it. It was giving us a false indication that there was no susceptibility or no interference. So this was a false pass, which to me is it's beyond bad. This is the worst possible outcome. If you actually have some interference or some susceptibility that you're not able to see because of the nature of how you're running the test, that's the worst possible outcome. So when you do apply the modulation, that brings out the susceptibility where the CW signal, clearly masked it. So just looking, if you've ever looked at any of these kinds of images from a detector system or imaging system, you'll see what's commonly known as this herringbone pattern. Okay, where you've got, I believe, the darker images where the perturbing signal is applied. So the 50 pixels on, and then the 50 pixels off is this lighter color, which that's got to be what it is, because it's consistent with this lighter color where you're probably switching to the next frequency in the scan. So and then this clearly shows up in the statistics. When you take your statistics of a frame like this, then you will obviously have more of a greater standard deviation, and it'll bring out the problem. If you're going to be susceptible at that given frequency, it's going to exaggerate it so that you will actually see it, and that's what you want. Okay. Now, another example is a pressure transducer, where the nature of the device is that it just typically provides just a DC potential as a function of the measured pressure. Right. And so the applied susceptibility signal will just ride on top of the DC potential. So if you apply the 1 kilohertz pulse modulation, you'll get a signal that looks like that. But if you apply a CW signal, that's what you'll get. You'll just get a CW signal riding on top of the DC potential. And in this case, the CW signal may be easier to measure and quantify your susceptibility. Okay, so if this is the case, you get to tailor the test method and specify that we're going to apply a CW signal instead of a modulated signal. But that's all about knowing thy EUT. If you know the device that you're testing, then you can make these informed engineering decisions about the best way to test it. So, if you ask me, what's the best way to test, with a CW signal or with a modulated signal? What's the answer? You should know that it's the same answer to any given EMC question.
It depends.
Thank you.
It depends.
Who said that? Who gets the gold star? Two of you get gold stars.
They typed
The
it
sec-
in.
The second one was Mike Garrett.
Shane
Mike,
over here at Langley.
I'm sorry?
First was Shane over here at Langley.
Okay. Shane at Langley and Mike, who? I
At
didn't miss-
GRC.
Okay. All right, gold stars for both of you guys. All right, it depends. So, all right. So just the traditional flow for frequency swept susceptibility scans, you have your starting frequency or just your nth frequency. But let's just say this is your first frequency. Well, then you ramp the applied signal level up to the desired level. And you want to start at some low level and then ramp the signal level up. Turn on the modulation. Dwell for 3 seconds is the default per mil standard 461G. Turn off the modulation. Then ramp the applied signal down, and you can set this in your test software. Any decent software worth using, or maybe you're doing it by hand. But whatever it is, you want to ramp the signal level down. We go down somewhere in range of 6 to 12 dB. And then step up to the next frequency, so f of n plus 1, or f sub n plus 1, then ramp the applied signal up to the desired level, and then rinse and repeat. Now, the tolerance for the desired level will affect your leveling time. So I recommend you can set your plus and minus levels for your tolerance. So I generally recommend, and we generally use at Goddard, minus 0 dB, so that you want the minimum of your specified level. You don't want to go below that. And then the plus 1 dB, that all depends on the test and just the nature of what we're doing. But clearly, if you specify a ridiculously tight tolerance, like minus 0 dB to plus 0.01 dB, it's going to take you a very long time to level on that. Right? It's going to come up to level, then it's going to overshoot it, then it's going to come back down, all that sort of thing. If you open up the tolerance, if you open up to 0 dB minus to plus 10 dB, well, it'll level very quickly, but then you've got a very wide range of what the applied level could be. So it's something you have to play with. Generally between maybe plus 1 and 2 dB, I think is what we generally go with. But I'd much rather have a slight over test than an under test. So that's the reason for the -0 dB. And then again, your mileage may vary. You just have to play with this with your own test system. And it's going to get tricky when you hit resonances in the room and stuff like that. That's what's going to make it a little more difficult or take a little bit longer to reach the desired level. And then I just emphasizing the point here, the level, the amount to which you reduce the signal before stepping up to the next frequency, that's also going to affect your time. Right? The further down in level you go, the longer it's going to take to bring it back up. But this is basically for safety, that if you don't bring the level down at all and then just step up to the next frequency, if you're starting to hit a resonance, then the applied level can go up very quickly. And if you hit a room resonance, then if you just step up to the next frequency without bringing the level down a bit, you can, if you're hitting a room resonance, that level can shoot up a bit, and you want to do that in a controlled manner, right? So that's why we bring the level down, step up to the next frequency, then bring the level back up. So this is the overhead that I was talking about beyond just the 3 seconds for dwell. This is the thing that we know about, and if you relax this to 1 second, then that'll tighten up your time somewhat. But the overhead could be longer than 3 seconds. This total time could be 6 seconds or even more, depending on these other parameters that are less well defined. Right, the dwell time is the thing you can directly control. This other stuff, less so. I was pointing that out. So review of polarization. Polarization is just in the direction of the conducting elements of your antenna. So this is vertical polarization. E plane is in the direction of the elements. H plane is orthogonal to that. And then just horizontal is just rotated 90 degrees. And then again, this is just more review that in the MIL standard, they specify that at least 2 meters of each interconnecting cable be routed to the front boundary of the setup. It's intended to ensure that radio emissions and susceptibility testing properly assesses the performance of the EUT. And just cables are part of the EUT. You can't get around that. I've got a review of antenna parameters here. Again, from before, I can go through this pretty quickly. Just directivity and gain. Directivity as a function of direction, as a function of the theta and phi angles, is defined as the ratio of the actual power and power density in a given direction to the power density from an ideal isotropic source transmitting the same power. So the isotropic power is just the applied power, P sub T, transmitted power, over 4 pi r squared, over the surface area of a sphere at a distance r. So that's a definition of directivity. And so the numeric is just how I've just described it, but it's usually converted into dB above isotropic, so dBi. And because you're talking about power numbers, it's 10 times the log of the ratio. Generally given as a single number at the maximum value or at your bore site of your antenna. And just directivity is related but distinct from gain. Gain is basically defined as directivity times efficiency terms. So you might have loss, impedance mismatch, and so on. There are different symbols used for these efficiency terms that I'm not really going to get into here. But just be aware that gain is directivity plus other things. So or multiplied by other things to be more precise. And then so your half power beam width or 3 dB beam width is just the angle between the two directions in which the power density is 1/2 or 3 dB down from the maximum power density of the beam. So this is what tends to be specified in antenna data sheets that we use to determine spot sizes and the number of antenna positions we need. This is clearly inversely related to directivity. The more direct the more directive the antenna is, the smaller or the lower the half power beam width will be. So this is the same guidance as RE102. So for RS103, for testing from 200 megahertz up to 1 gigahertz, place the antenna in a sufficient number of positions such that the entire area of each EUT enclosure and the first 35 centimeters of cables and leads interfacing with the UT enclosure are within the 3 dB beam width of the antenna. And then above 1 gigahertz, you want to place the antenna in a sufficient number of positions such that the entire area of each EUT enclosure in the first 7 centimeters of cables and leads interfacing with the EUT enclosure are within the 3 dB beam width of the antenna. So again, cables are part of the EUT. Okay. Just to hit you over the head some more with that. So your spot size, this again is a carryover from RE102. I mean, the spot size, the general concept is the same for emissions and susceptibility. But it's determined by that 3 dB or half power beam width of the test antenna. And it's just basic geometry, right? They're going to specify this full angle here, you know, from one edge of the beam to the other. I mean, it's not really an edge, but you know, it doesn't just fall off the cliff here. But that's how we define it is you know, from minus 3 dB point to the minus 3 dB point over here. So you would basically take half of that angle, so you're getting the angle on either side of the bore sight line, right? And then you take the tangent of that angle and then multiply by your distance r, and then multiply by 2 to get the total spot diameter. Okay, it's just basic geometry, and that enables you to calculate the spot size for a given 3 dB beam width and a given distance. Given distance of your measurement antenna from the EUT. Okay, and then that'll help you select an optimal number of antenna positions to provide sufficient coverage while making efficient use of test time. For RE102, since the scans are generally pretty quick, if you're a little, you know, if it's not real clear whether a given number of antenna positions is enough, well, okay, just adding another antenna position is going to add some test time, but kind of, you know, an incremental amount of test time that is probably going to basically be in the noise, as it were. So for RE102, like erring on the side of one more antenna position is generally not a big deal. RS103, the test times are much longer. It is the longest. I think it's the biggest time consuming test that we have. So every antenna position that you have can add hours or maybe even days to your test program. So it's really much more important to optimize your antenna positions for RS103. You know, and every position really needs to be value added, and this helps you do that. Now, one thing that helps this, that works to your advantage, is that and here's another commercial for using the latest version of a standard, right? Specifically, MIL standard 461G allows larger distances than 1 meter between the transmit antenna and the EUT boundary. This approach is actually preferable where amplifier power is available to obtain the required field, since more of the EUT is illuminated at one antenna position. Okay, if you insist that you're under contract for 461F or E or D or basic going back to 1967, you're missing this bit of guidance that actually helps you do your job more efficiently. So the spot size diameter scales directly with the distance R, but then note that the power that you need to get an entire, provide a given electric field will scale with the square of that distance R. So just for example, if you move the antenna back to 2 meters, that doubles the spot diameter, but you need 4 times the power. 3 meters triples the spot diameter. Now you need, well, almost 10 times the power, 9 times the power to deliver the same electric field. So this approach helps to optimize misprint there, optimize the number of antenna positions in order to provide sufficient coverage of the ET and interconnect cables while making most efficient use of test time. Now, here are the figures showing probe placement. No, I moved this. I moved this chart. My apologies. Shouldn't be continued. And while I'm fixing things, I will fix that. All right. These are a couple of pictures from these are the diagrams in the mill standard showing antenna positions. This can be a little misleading, where it kind of implies that you can put the field probe in front of the EUT, and you really shouldn't do that. Because we had a situation some years ago where we put the field probe in front of the EUT. Well, we had reflections coming off of the EUT that, in that case, provided constructive interference that showed us that the level we were flying a much higher level to the EUT than we thought we were. I mean, to state the obvious, you have to remember, all you have to go on is what the field probe is telling you. And all it knows is the field level that it is seeing at that particular location. So that's all you ever get, right? It's like a temperature sensor that's right on your engine in your car might tell you it's 140 degrees when, because that's how hot your engine is. That doesn't mean it's 140 degrees outside. So so you have to be very careful about where you put field probe, and this is not optimal. So we learned that in a test about 10 or 12 years ago. So you want to put it off to the side, in basically the same distance from the antenna as the EUT. So it's just an unfortunate way that they drew the diagram in the mill standard. So I redrew it here to make it a bit more explicit, and keep it within the 3 dB beam width of the antenna, and for following the guidance in the mill standard, from 200 megahertz up to 1 gig, you want to encompass the first 30 centimeters of cable, from coming out of the EUT, and then for 1 gigahertz and above, it's the first 7 centimeters of cable. So we'll look at a couple of example antennas here. We look at the large double ridge guide antenna. The 3106B is the one we use at Goddard. So the data sheet specifies this up to 2.5 gig. We're only using it up to 1 gigahertz. So this is the range of concern for us. So the worst case beam width in this frequency range, looking at both E and H plane, because H plane is orthogonal, so you have to pay attention to both of these, right? You might think, well, we're measuring electric field, so we only care about E plane. Well, that's not really true. When it's in this orientation, when it's in vertical polarization, that beam width is specifying in this direction, and then the H plane is specifying in this direction. So how much of the horizontal direction that you're getting of your test setup. So you really need to pay attention to both of these. So I generally use, the worst case of both plots. So they're specifying 30 degrees or plus or minus 15 degrees from bore site. So your spot size at 1 meter is 53 centimeters. You get double that if you move it back to 2 meters, right? But now, a couple other plots that you'll see in the data sheets for these antennas are antenna factor and gain. Here they're putting them on the same plot. So the minimum gain, and we'll get into gain here in a little bit. The minimum gain here is just at the low end here is 5 dBi or 3 numeric. In the calculation I'm going to show you, we need to use the numeric value of gain. So we've got to convert that to numeric. And then just for additional information, I'm showing the VISWR curve, the voltage standing wave ratio. It's a measure of impedance match or mismatch to 50 ohm. And the closer it is to unity, the closer the input impedance is to 50 ohm. So this one's not bad. This one's pretty good. show you an example of a worse one here in a little bit. So this is the small ERG antenna. So we look at this. We've got the worst case. Well, at just looking at 2 gigahertz, you know, at our S band range, the beam width is 50 degrees, so plus minus 25 degrees. But then it goes way down to 22 degrees up at the upper end. I should have put 18 gigahertz here, but at the upper end, we're way down to 22 degrees. So you might think, well, okay, we've got to define all of our antenna positions based on that worst case beam width of 22 degrees. But wait, hold the phone on that. Again, your mileage may vary, but at Goddard, for RF testing, for our RS103 testing above 1 gigahertz, we have this bank of amplifiers here that breaks the frequency range up as shown here. The top one goes from 1 to 2 gigahertz, generally in factors of 2, except for the top one. So 1 to 2 gigahertz, 2 to 4, 4 to 8, and then 8 to, great. I was thinking so much of the factors of 2. That's 8 to 18. Okay. So the specific numbers are less important than just the fact that that you've got a different amplifier in each of these frequency ranges. So each amplifier must be warmed up and connected individually. So like you do your 1 to 2 gigahertz scan, and then you disconnect the cable. Okay, so each amplifier must be changed at each frequency break. The antenna positions may be adjusted in each frequency range according to the spot size. So there's no need to maintain a constant set of antenna positions over the entire frequency range. You've got some flexibility here to say, okay, while we're changing the amplifier out, we can go ahead and move to a different set of antenna positions as we need to, as the spot size gets smaller. Okay, so so we'll go back to that antenna here in just a moment, but well, yeah, my apologies. I moved some charts around here this morning, and that's one maybe I should have left after this one. But let's look at this one here. So yeah, just going back to the 3117 here. If we look at the different frequency ranges here, so in the 1 to 2 gigahertz range, our beam width is 50 degrees. 2 to 4, it's actually a little bit larger. It's about 60 degrees. 4 to 8, it goes down to about 40 degrees, and then from 8 to 18, that's when our worst case is the 22 degrees. So if we want to include more antenna positions to get better coverage in this higher frequency range, we can do that, but we don't have to do that in the lower frequency ranges where we've got we've got bigger spot sizes. There's no particular reason to increase the number of antenna positions, which is going to increase the amount of scan time where we got these nice big spot sizes down here. And then there's another thing here on the gain curve. Our worst case is 5 dBi or a little over 3 numeric. 4 to 8, it's 8 dBi or a little over 6 numeric. And then from 8 to 18, it's 12 dBi or 15 numeric. So that's where this previous chart comes in. I was grappling with the order in which to show this, but it's important to know how to relate your transmitted power to your radiated electric field, at least the first order. So the power density piece of D of a plane wave, I mean we're doing we're considering this to be an ideal plane wave, coming from a good distance from a point source. So there's an approximation here, but it's a decent approximation. So The power density of a plane wave as a function of the electric field intensity E in vacuum or air, where the wave impedance is 120 pi or 377 ohms. Well, it's just E squared over the impedance, 120 pi. So, but then the power density at a distance R from a transmitting antenna with gain G, just the very definition of that is if you take the transmitted power from, or the power density from an ideal isotropic source, that's the transmitted power divided by 4 pi r squared. And then we multiply by the gain to get the actual power density of, of that, that incoming wave. I mean, that's the very definition of gain. Okay. So we have these two expressions for piece of D for power density. Well, we can just set them equal to each other. And then we can first solve for piece of T for the transmitted power that you need to get a given electric field intensity at a given distance for a given gain of your transmit antenna. And then we can rearrange the terms differently to solve for the electric field intensity as a function of transmitted power. So these are two very useful equations. Once you use them enough, you'll just remember them, but you can always get back to them just knowing this relationship here, which is what I generally do. I like to minimize the amount of stuff I have to memorize because I suck at memorizing. So, but your transmitted power is E squared R squared over 30G, and then your electric field is the square root of 30 times piece of T G over R. And you can see these are just equivalent expressions with terms rearranged. So just looking at a couple of examples, if you want to get 20 volts per meter at a distance of 1 meter, and I'm going to use that example of a gain of 3, one of the examples on the previous slides, you need about 4.5 watts. So a 10 to 20 watt amplifier is recommended. And then if you move the antenna back to 3 meters to get a larger beam width for the same antenna gain, now you need about 40 watts. Right, about a factor of 9 more power. So there you'd want about a 1 to 200 watt amplifier to get that power. Right now, this is not considering cable losses, room resonances, and so forth. This is meant only as a starting point. But I think this is a very simple pair of equations to use to at least give you a starting point of how much power are you looking at to get a given electric field level? And then you can add in your cable losses and room resonances and stuff like that to know how much overhead you need. So, so we walk through this example. So basically summarizing all the concepts I just went over, a large spot size provides UT coverage with minimal antenna positions and makes most efficient use of test time. That's great. That's your ideal. If you've got a spot size on the order of 50 or 60 degrees, and you're just testing a box, you probably do that in one antenna position, and that's great. But as gain increases, the spot size will decrease for a given distance from the UT in general. But it allows for the placement of the antenna further from the UT to increase the spot size. So it's a little bit of a balancing act. Right, and it is frequency dependent, and antenna positions can be modified in different frequency ranges to accommodate your needs. Amplifier power should be used that provides sufficient headroom over the needed power while posing minimal risk to hardware. So that's where just when you determine how much power you actually need. You want to make sure you have enough headroom, but not too much. You don't want to use a 1,000-watt amplifier where all you need is 10 watts to run your test. So there's some examples on the previous slide. But to take this a step further, if available amplifiers, I mean, you're going to be limited by what amplifiers you have in the lab, right? So if available amplifiers have significantly higher power than what you need, then attenuation is recommended to reduce that available power. Okay. And I have another typo there. So again, looking at our example where we needed 4 watts, or so a 10 or 20 amplifier was what we recommend. Well, if all you have is a 1 to 200 watt amplifier, then put a 10 dB attenuator on the output there. The ultimate risk is, you think you have software control, right? Well, our software is going to limit how much power we provide. Well, that's all well and good, but software can fail. I know that's kind of a radical, wacky thing to say, but you know, punch in something that takes your drive circuitry to the maximum level it can put out. So if all you need is 10 watts and you've got a 1,000-watt amplifier sitting there, 100 watts in the damaging. So if you're going to put an attenuator in the system, a fringe benefit is that you can place it at the antenna input as opposed to directly on the output of the amplifier. I mean, electrically, you would think, well, what's the difference? And electrically, that's true. But if you're going to put an attenuator in place, if you put it at the antenna input, that will minimize the impedance mismatch. Because antennas do not always provide a good match to 50 ohms. Some of them suck. And that's the example I'm going to show you here. Look at the VISWR curves on data sheets. So if you are going to use this biconical antenna, if you're kind of forced into it because you've got a transmitter operating below, in that 30 to 200 megahertz range, the VISWR of the biconical antenna really sucks below 60 megahertz. I put crappy on the chart. Maybe I should have put sucked just because. But I mean, this is I believe this is numeric, but the VISWR is above 10, and we said 1 is the ideal. One means you got a perfect match to 50 ohms. So below 60 megahertz, this thing has a VISWR of over 10, and it's pushing 100 down at 20. So we're only going to about 30. So about 20, a factor of about 20 here. This is terrible VISWR. This is another reason why these are terrible antennas. They're very difficult to use, especially down at this lower frequency range, because of this VISWR. They're very efficient. You got to put a lot more power into these things to get a desired field at the low end. Okay, so if you're going to use this thing, then and you have a lot of amplifier power available, you put your antenna or pad right here at the input to the antenna. It will minimize that impedance mismatch if you actually need to use this crappy antenna for your test. So, I've included the stuff about alternate antennas here to carry over from RE. Again, pretty much any antenna, certainly theoretically, any antenna can be used for both receive and transmit. Some are better suited for one application or the other, but that many of these antennas we can use for either emissions or susceptibility testing. So I've gone over some of the advantages and disadvantages of log spirals and log periodics. But I think I'll just pass over this. They do offer a larger field of view, and you get both polarizations at the same time. No question? Is there a question? If not, can you please mute your mic? Okay. I think we have a few minutes before our tornado drill, so let me go over probe placement. What do we got here? Oh, it's 10 o'clock now, so I'll talk real fast. The drill may start any moment. But so just talking about field probe placement, you want to place it at the same distance from the transmit antenna as the UT. Don't place it directly at corners or edges of the UT components. Below 1 gigahertz, you want to place it a minimum of 30 centimeters above the ground plane, within 35 centimeters of the UT horizontally, we talked about earlier. Above 1 gigahertz, place it at a height corresponding to the area of the EUT being illuminated and within the 3 dB beam width of the transmit antenna. And we talked about how to calculate that. Place one edge of the EUT as close as possible to the edge of the beam to maximize exposure to cables and to maximize available space for probe. And the available space adjacent to the EUT depends on the size, of course. Then if a larger beam is needed, the transmit antenna may be moved further away from the EUT, and you have to make sure you've got enough amplifier power to deliver that desired electric field, as we talked about. So there's another option is, I'm just going to talk about this in general terms here. Another option is to pre-calibrate the field, which ideally would be done before you bring the EUT into the EMI lab. So you would place your electric field sensors or a receive antenna in the location where your EUT would go, and then basically run a scan as though your probes or your receive antenna are your EUT. Just run a scan and then determine the power levels that are needed to establish the desired field at each frequency. Then you put your EUT in place and then just play back those power levels. There's differing schools of thought on this. It's generally more recommended for a larger test article, like a system level test. But my general take on this is that I think it's actually a more realistic and more representative test, because if you think particularly like for a launch site test, a radius susceptibility level from a launch site transmitter. That transmitter is just transmitting power. It's just transmitting power and broadcasting that signal over the entire area that where that's exposed to it, right? And there's no electric field sensor at your spacecraft on the launch pad where that level is being adjusted to provide some desired field level at that particular location to account for any reflections or any constructive, destructive interference that might be providing a different level at that particular location than any other in the area. The transmitter is just transmitting power, and anything that's any perturbations to that distribution of the field by the presence of the EUT are irrelevant or inconsequential, right? The transmitter is just going to transmit whatever power it has, and there you go. So as I got more familiar with the pre-calibration method and we've implemented on a few tests, I've kind of come to the conclusion, or at least my own belief, that it's a more representative way of testing for that very reason. Right, your whatever your transmitter is, whether it's an onboard transmitter, on your spacecraft or at the launch site, wherever it is, it's just transmitting power. And we've seen, in many of our tests where, the placement of the field probe is going to determine the level that you see, right? The RS103 is an imperfect test. You're going to get some distribution of the field in your test chamber. It's not an open area test site. You're going to get reflections in the room, whatever. You move the field probe a few centimeters or several inches, whatever system of units you like. The field level will change somewhat because of the presence of the EUT and the reflections off of it and everything else are going to affect the distribution of that field in the chamber, and certainly in the area around the EUT. And the pre-calibration method makes you less susceptible, as it were, to that. Right? You pre-calibrate the field, then you just know that you're transmitting this amount of power as a function of frequency, and you just play those levels back. And you don't really have to be concerned with trying to attain a specific level with a field probe in a specific location. So there are different schools of thought on this, and even if we're doing a pre-calibration test, we'll almost certainly still stick a field probe in there just to get some indication that we are indeed applying a field. And if it's truly a pre-calibration test, then we're not going to be leveling on it, but we're just going to monitor the level that we're getting from the electric field probe just to verify that we are indeed transmitting something. So that's my take on pre-calibration. It's another option available to you. Nobody's telling you that you have to do this, but it's another available tool in your toolkit, and it can. I think it can actually be a better way to test in some cases, and again, particularly at system level, large test articles and things like that. I think I just heard a few beeps from some of the emergency equipment out in the hall. So the emergency test might be over. So there we go. All right. So a few words about survive without damage launch limits. So Goddard projects, and I think this is fairly typical of NASA projects in general, apply two sets of limits for radiated susceptibility. So there's on-orbit operations and then separate set of limits for launch site and launch vehicle. So for equipment that is powered on at launch, then the limits I really would say, must be verified by test. But for equipment that is not powered on at launch, then the requirement is to only survive these levels without damage. So to my mind, this really cannot be verified by test. If you apply a level with the unit powered off, and then you turn it on and run a functional test and see that everything is working, all you have verified is that you didn't break it right then. You really have done nothing to verify that you didn't cause some kind of latent damage or walking wounded or what have you that could bite you 6 months or a year from now, or worse, you don't see anything until it's on orbit. I think you must inherently verify survive without damage, at least in part by analysis. So the mechanism is that an incident field induces a coupled potential and current onto some element of the UT. So, for example, cable, connector, improperly sealed seam, and so forth. And the two main coupling models are the transmission line method and the dipole method, which is what I'm going to talk to you about now. So the transmission line method, we get what we need here basically from CS114. So the field to wire coupling, I discussed at length in the CS114 section. The CS114 limits are specifically intended to correspond to different RS103 limits. So, but the coupled potential in the plateau region of these curves, so that's the worst case. The coupled potential as a function of electric field is 150 millivolts per volt per meter, and I discussed and provided the derivation of that in the other session, so I'm not going to go through that again. And then the current, the coupled current as a function of electric field is 1.5 milliamps per volt per meter, and that actually is stated in the mill standard as what the level is in the plateau region of all these curves. So for a 20 volt per meter example, a typical launch site level, that corresponds to curve number 3. And it says in the mill standard that curve number 3 is equivalent to an RS103 limit of 20 volts per meter. So just using these conversion factors here, if you have unshielded power leads, so then the worst case coupled potential, common mode potential, is going to be 3 volts, right? Just 20 volts per meter times 150 millivolts per volt per meter. You're going to get a worst case common mode potential of 3 volts. If that's a power lead, because that's the only thing that should be unshielded, 3 volts on top of a 30 volt power lead should pose no damage concern. So for shielded cables, that's going to give you 30 milliamps on the shield, just 1.5 milliamps per volt per meter. And if you use a worst case transfer impedance of your shield of 1 ohm, and I've got charts and a write up on that separately. But just going with that worst case transfer impedance of 1 ohm, that means you'll have a worst case coupled potential on your signal leads inside that shield of about 30 millivolts. There again, that's a very benign level unless you're talking about extremely sensitive circuitry, and if you are talking about anything that could be possibly damaged by levels that low, you need to improve your shielding, right? But by and large, just any normal circuitry, 30 millivolts really shouldn't be anywhere close to any kind of a damage concern. And then the dipole method at higher frequencies, so above about 600 megahertz, the effective height, I went through this in the dipole session, the effective height of a tuned half-wave dipole, that's the best you're going to get, right? If you're actually exciting it at a half wavelength resonance, the effective height is going to be lambda over pi, or rewrite it as c, the speed of propagation, speed of light over pi times the frequency. Now, note that this decreases with frequency. Okay, so at higher frequencies, the coupling gets less efficient. So that works to your advantage. So the worst case open circuit common mode potential is going to be just the incident electric field multiplied by this effective height, right? Your lambda over pi. And then the output impedance of a half wave length dipole, and I went through that in the dipole session, that's about 73 ohms. And that you'll find that in any textbook about antennas and dipoles. So the worst case common mode current that will be coupled from an incident wave is then going to be the common mode potential divided by 73 ohms. So if we look at our typical launch limit, again, 20 volts per meter from 1 to 6 gigahertz. For unshielded power leads, your worst case potential will be just under 2 volts. Again, 2 volts on top of a 30 volt power feed should not pose a damage concern. And then for shielded cables, you're looking at about 26 milliamps coupled onto the shield, again with a 1 ohm worst case transfer impedance, about 26 millivolts on your signal leads. Again, shouldn't pose any real risk of damage unless you're talking about extremely sensitive circuitry. So that's for 20 volts per meter, and so of course if you have higher launch site levels, I mean things will scale accordingly. But this gives you an idea that you're generally not talking about any serious risk of damage unless you're upwards of 100 volts per meter. 20 volts per meter, 30 volts per meter, 50 is generally not something that puts you in the realm of a damage concern. All right, the last thing I'm going to talk about here is an honorable mention of reverberation chambers. To say that I have limited experience with reverb chambers is being a bit generous. I mean, I've stood in one, but I've never actually conducted a test in a reverb chamber. So, but here's a diagram. This is right out of the mill standard here, but the chambers that I've seen pictures, and the ones that I've actually stood in. There are these paddles here that will turn, and the idea is that it basically, I guess, mode stirring is a term that's used. It's that these paddles are turned in real time to stir up the modes and just change the field distribution in the chamber as a function of time. Okay, so I'm not going to say much about these because I am far from an expert on these types of chambers, but Mill Standard 461G Section 521.4 provides guidance for performing RS103 in a reverb chamber. But clearly a dedicated facility is required for this, and we don't have one at Goddard. The facility that I've stood in is at Langley. They may actually have 2 of them. And so if there's anybody from Langley who would like to comment on this, please chime in. And at any other facility that actually has a reverb chamber.
So yes, Langley does still have a couple of reverb chambers over in, used to be the Herf lab, now the Weiser lab. We haven't actually used them for mill standard testing because it falls under the research directorate and their kind of thing, and they haven't really had any work for us yet.
Okay.
So it's there. I don't think anybody in our actual EMC testing has ever used it, at least for 461.
But I think it's fairly new, right? Wasn't it built in the last 5 or 10 years?
Within the past 5, I believe it was part of that new building.
Okay.
And I will withhold further comment on that.
Okay. I mean, I came down to Langley right before Courtney Rollins retired, and I specifically came down there to hang out with her for a day right before she retired, and you know, to see some of these new facilities, including that new reverb chamber, and it is pretty cool. They actually moved the paddle for me upon request. They weren't testing anything in there, but
Right.
and you can adjust the speed of you know, the speed of rotation. I don't remember what the maximum speed is. Obviously, you're not going to be like, it's not like a reaction wheel or something like that. It's not like hundreds of RPM. But but anyway, just a few last little comments here from the mill standard. I'm just going to read the highlighted bits.
Hey, John,
Yes.
this Ed. Just want to make a comment that I believe the fan in the microwave oven acts as a remote stirrer also.
Yeah, I believe it does. Yeah. Right. So yeah, you've got a reverb chamber in your kitchen probably. So, but this is my last chart, so I'll just read this stuff and then open it up for questions and discussion. But so a couple of the advantages, just reading the stuff I highlighted in blue. Any physical location in the chamber will achieve the same peak field strength at some position of the paddle wheel. The orientation of EUT enclosures is less critical since all portions of the EUT will be exposed to the same peak field at some paddle wheel position. So those are the selling points of reverb chambers is that yeah, the specific location in the EUT is not critical. It's basically going to get the same level wherever you put it in the chamber. But some issues with reverb chambers are as follows: the field polarization and distribution with respect to the EUT layout are generally unknown at a point in time. If a problem is noted, the point of entry into the EUT may not be apparent. So, now that's yeah, to a degree, that's kind of a common issue with rated susceptibility testing in general, right? I mean, as compared to like you know, a common mode conducted susceptibility, CS114. Now, obviously, we only do that up to 200 megahertz. But if I'm injecting on a specific cable, and I see a susceptibility while I'm injecting on that specific cable, well, then I can conclude that there's something about that interface, you know, the interface circuitry that's running in that cable, that the susceptibility is associated with that circuit, with that interface circuit. So I can localize what the problem is with a test like, you know, with a test like CS114. With radiated testing, well, specifically radiated susceptibility testing, well, with radiated susceptibility testing, I mean, the nature of a susceptibility is going to tell you that the susceptible circuit, that's where your susceptibility is manifesting itself, but you still may not know exactly like how the energy is getting in to corrupt the circuit in question. So I think there's some amount of that uncertainty that's built into the nature of the test, and I think the point of this statement here is that you have a little more uncertainty with the reverb chamber method, that the specific nature of how the energy is coupling in and causing a perturbation to the UT is there's a bit more uncertainty with that. That's at least how I'm interpreting that statement. Again, I am not an expert on reverb chambers. I just wanted to mention this, that they are out there, and they you know, Langley has one. So, you know, if you are interested in running a test that actually uses one, then, you know, happy to put you in touch with the folks at Langley and see if you can make some arrangement. So that is what I have. Anybody have any questions or concerns or discussion points? Is anybody still there?
Hey, John, Wayne here. This is maybe a little bit off the subject. I can't even relate, but you had touched on a point about, you know, the quarter wave antenna, and about maybe a year and a half ago, I was supporting this program for very brief, maybe a couple of months, and they changed direction, and it was basically a program called Roses 2. And they were basically trying to measure the flux on the surface of the moon. And one of the things with this, I know them say it's a little bit off the subject, and because I heard you kind of touch on a similar subject matter. In this case, is how to mitigate it, the effects of you know, EMI. But in this case, you have a antenna. I didn't go as far into the details in terms of what the characteristic of that antenna was, but it was similar where you just couple the flux and then, you know, basically amplify signal condition and bring that signal into a DSP to do the processing. And so the question was, I think you mentioned the impedance of that antenna. So I guess I'm missing my train of thought, but how would you, you know, a situation like that to optimize that application? Because in what you're speaking about is how to mitigate it. But how could you utilize that? Because one of the biggest thing, what I discovered, that no one knew what the impedance of the antenna was, and the interfacing circuit that I was proposing was a differential circuit to measure this flux, and it's this signal that's coupling on the antenna, and you want to. And my goal was try to shape the noise before it goes into the ADD converter, so minimize aliasing. So on the antenna part of it, I wasn't so sure about what the optimum design should be so that we don't attenuate the signal, but optimize the signal. I don't know if that's way off topic for this, but I just was curious.
Yeah, I think I'll have to talk to you offline about that, because I'm not entirely, not entirely sure how to address that at the moment. But it sounds like an interesting problem, but yeah, we can talk offline about that.
Yeah.
Okay, anybody else have any questions or comments, parting thoughts? Okay, well, I'm happy that the tornado drill didn't disrupt things. It would have made the video recording a little bit interesting. But fortunately, that's not something I have to grapple with. So it doesn't sound like anybody else had to vacate their buildings for a tornado drill either. So hey, we'll call that a plus. If nobody else has anything, thank you very much for participating again. We'll do the lab portion on Monday. At least that's what we're shooting for. Got to get with the lab guys to make sure we get everything set up, but I think we'll be able to do that. And if so, we'll talk to you on Monday.
Thanks, John.
Thanks very much.
Have a great day.
And
Thank you.